All right, we're going to take a look at a new unit and some new material now. So what I have for you is I have this shape. And gosh, it would be great if you could find the area of that shape for me. Now you might look at that and go, gosh, what did I use in geometry that would find the area of that particular shape? I can't think of it right now. Well, how about another one? Surely you remember some geometry formula for the area of that region right there. No? All right, it's 0 for 2. But could we approximate the area? Let's go back to our first one. Now, you might look at this and go, well, it's kind of like a semicircle or a quarter circle, I guess you could say. Or maybe I could break this into a triangle, like maybe like right there. Oh, but then I got that shape left there. Or what if, well, it's not quite a square either. What if I put it on graph paper and just counted squares? That's an option. Let's go back to this one. Well, it's kind of like a triangle if you went from one corner to the next, but we've got all these wavy things here we have to account for. Well, there's no geometry formula for this. But if we happen to know the function that made this curve, or the function that made this particular curve, we'd be able to do it. If we had a mathematical model that we could use for the top part, because what you'll notice about both of these is they have at least two sides that are completely straight. So we can think of each of these as like this is the origin, this is the x-axis, the y-axis. And so what we're actually finding is the area under a curve. Now, what if I could find the area under this curve, but then what if I took this area and I rotated it around this pencil? Like, here it comes towards you, and there it goes, creating the third dimension, which allows us to find volume. So what we could do to find the area of this using our geometry skills is we could try to break it up into shapes that we have knowledge of: triangles, quarter circles, semicircles, rectangles, or squares. Heck, maybe we could just fill this all up with squares that are a certain dimension and get really, really close. But I don't want to be close. I want to be exact. And so that leads us into our next topic. And if you recall, what we did before for most of this course is, we did limits, obviously, but with limits gave us derivatives. And when we took the derivative, we ended up with what's known as a differential equation. Now, a differential equation is basically an equation that has a derivative, like f prime of x is a differential equation. F double prime is the second derivative, it's also a differential equation. We call this a first order, a second order. We could even do a third derivative, and that's a third order diff EQ. Almost kind of sounds like Star Wars, the first order differential equation. But what if I know the derivative and I want to go back to the function? Well, that's really what I want to talk about. I want to find what's known as the antiderivative. Antiderivative. Kind of the opposite of deriving. Okay. For example, let's say that f prime of x is equal to 2x. And we want to find what the function was. Can you think of a function that has a derivative of 2x? I can. I can actually think of a lot of them. You're going, what do you mean by a lot of them? Well, x squared would work, wouldn't it? So would x squared plus 1, or x squared plus 17, or x squared plus 173. If we take the derivative of all of those, including this that you see, the derivative is 2x. We call this by a different name. And so what we can say is we can say, well, the answer to this is really x squared plus some constant. That's really what f of x has to be. Okay. And we say that this is the solution to the differential equation. I'll abbreviate diff-EQ. You might have heard that class. It's a nice little semester-long college class. Very interesting. So there's multiple solutions to this. So, and what do they look like? Well, they look like this. They look like this parabola, or all the parabolas that you see on screen, and not even on the screen. They all involve x squared plus some constant. So what else do we need to know? Well, we have to have knowledge of like another point, like say, I don't know, let me just pick one. 1, 4, let's say. Is there a differential equation? Or is there a solution to a differential equation that passes through that point? Maybe x squared plus 3 would do it. Okay. That's 1, 4. That solution runs through it. Okay. Every time I pick a different point, I'm going to have a different antiderivative based on the information that I have. Okay. So think of physics. If you know velocity, okay, and you have to find the position function, if you could find the antiderivative of velocity, that would give you position. My goodness, if we knew acceleration, if we could find the antiderivative of acceleration, that would take us back to velocity. And the antiderivative of velocity, again, is position. Oh my gosh, it opens up a whole bunch of stuff, doesn't it? So the antiderivative basically leads us into here. And when we do differentiation, we also know how to do integration. See, back in the day, you learn how to add to go one way, but then you learn how to subtract right after. That's what we're doing here. We're learning how to derive, find the derivative of a function, and then we're going to integrate to find the antiderivative and figure out where we started. So, integration. It's like finding the antiderivative. Okay. So, and I'll define it like this too. It's the process of finding a function for now, given the derivative. Integration, the process of finding a function given the derivative. Now, surely there's some meaning to integration. Well, there is. But let me share with you the symbolism that we use. We use this symbol for integration, and it looks like this. It's a very compressed S. And we call this the integral. And what's inside of here is, for example, let's say, it could be a function. It could be, let's say we've got a derivative inside here. And we put this dx with it. Now, dx tells us that it's with respect to x. Okay, we're integrating with respect to x, or with respect to y, or whatever the variable happens to be. Now, if we integrate the derivative, that would give us a function back plus some constant c, and that can be all wrapped together as well. Okay, so we write it like this: the integral of 2x with respect to x would be x squared plus some constant c. What does it mean? Well, let me show you. See, derivatives mean slope, the change in y over the change in x. So I made something for you. Look at this. Okay. If we take a look at this right here, okay, we're trying to see, using secant lines and limits, what the slope of the tangent line would be. That's really what we were doing. We were taking the change in y divided by the change in x. But now look at this. This is a curve. And I've put all these rectangles underneath the curve. And the more rectangles I use, notice the area begins to fill up. As n gets big, as the number of rectangles gets really big, I get really close to the area under the curve. Aha. Okay. So consider that. Consider this. A little side note here. Derivatives work with slope. Therefore, it's the change in y divided by the change in x. Now, if integration undoes, however you want to say that, a derivative, then an integral is going to be the change in y times the change in x. So what does it really mean? The integral represents the area under a curve. Why? Well, think about it. Over here, this dx is how x is changing. We'll talk about that soon. This is dy. This is how the y is changing. This is how the x is changing. X times y, which represents area. Okay, that's a little background story on integration. Now, it has many, many applications, but it also has a rule, one major one. See, derivatives had a power rule, a product rule, a quotient rule, a chain rule, trig rules, all this stuff. And integration, to go backwards, we have a few. Actually, we have tables and tables of ways in which we can integrate. We have their own methods, and some of those you learn in this class, some of those you learn in future classes like Calculus 2, Calculus BC at the high school level. So let's say we are integrating a constant with respect to x. Let's say we want to find the integral of 7 with respect to x. And let's make our own little rule for this. So we have to think to ourselves, okay, what can I take the derivative of that would give me a 7? Well, 7x plus some constant c. If I take the derivative of 7x, I get 7. If I take the derivative of a constant, I get 0. Yes, it checks. You have a way to check now. So in general, if we integrate a constant with respect to x, our answer is going to be that constant times x plus some other or same constant c. And we'll find c. It's called the particular solution eventually. So the integral of a constant like e, just e, or pi, just pi, or 7, or -3 is going to give us that. But we have a power rule for integration too. It goes a little something like this. Let's say we integrate x to the n power with respect to x. And n is a number. X is a variable. So variable right here. Okay, so think. X squared. If I had x squared and I had to figure out what we started with, let's see, I'd have to think of it in the reverse order, wouldn't I? So here is that reverse order. Here's what I do. It's going to be a fraction. I'm going to add 1 to the exponent, and I'm going to divide by that new power and add c. This is my rule. This you need to know. And it'll take a little time to get your brain adjusted from doing derivatives to integrals, but you'll get there. You'll get there just fine. So let's look at some scenarios with this if we could. In fact, let's integrate a whole bunch of things together. Like this. Well, before we do that, let's do this. Let's just show you kind of a basic thing, show you how it works. Okay. So here's what we've got. The integral of 6x squared. So here's what you do. What I would do is I'd keep the 6. And the rule says add 1 to the exponent of x, which makes it 3, and divide by the new exponent, plus some constant c. Now 3 goes into 6 2 times, so this is what I end up with. 2x cubed plus c. Does it check? If I derive that, do I get 6x squared? You better believe I do. How about that? So now let's do this. Now, we know if we have sums and differences when we derive, we can just derive each part separately and be okay. We can do the same thing with integration. So let's say we have 1/2 x cubed minus 6x squared plus 5 times the sine of x minus the 4th root of x cubed plus 4, all with respect to x, and we have to integrate that. What that means is we have to integrate that or find the antiderivative or solve the differential equation. Think this could be a derivative right here. So here's what I do. We're going to take it piece by piece. Everything's added or subtracted. So first step, 1/2 x cubed. Let's integrate it. I'd bring down the half. Now x cubed, I would add 1, divide by the new power. Okay, and I'll clean that up. That's really x to the 4th over 8, or 1/8 x to the 4th, however you'd like to write that. Show the power rule again so you can see that here. All right, next part, -6x squared, just like we did up top, minus 6, add 1 to the power, divide by the new power, gives us minus 2x cubed. And you'll get to the point, it might take a few days, but within a week, you'll just be rolling with things. Oh, what do we do with trig? Because the trig function doesn't really fit the power rule, does it? It's not a polynomial. Or in this case, we're not dealing with an exponent here. So what do? Well, we have to know our derivatives, frontwards and backwards. So we have to think to ourselves and go, okay, well, this is 5. And I have to think, what could I take the derivative of that would give me sine? Cosine's close, but it'd have to be negative cosine of x. The derivative of cosine is negative sine. To compensate for that sign, I'd have to make it the opposite. Now it's positive sine. And that's going to simplify to minus 5 cosine of x. Next part. Well, I first of all would have to rewrite this. This is really x to the 3/4. Okay, so when I do this, it's going to be minus. I'm going to have x, and I'm going to add 1 to 3/4. If I do that, I have to add 4/4, which makes it 7/4. And yes, you do have to have knowledge of fractions off the top of your head. You're in calculus. You can do that. Okay, divided by the new power. Now, I can't leave a fraction inside of a fraction. So what we've seen all year is when that happens, that we're dividing by 7/4. That's the same as multiplying by 4/7, and we get to here. And then we have a constant. Its derivative is just 4x. We bring that down plus some constant c. This is the antiderivative. This is the solution to the differential equation. Another name that we'll sometimes use is, we'll refer to this as an indefinite integral. It's indefinite because, yes, this is the antiderivative, but it doesn't represent like a number of something. It doesn't have value yet. So eventually we'll find what's known as a definite integral. Now, when you get here, you go, oh my gosh, do I have to find common denominators? The answer is no, you don't. We'll leave them just like that. So I'd like to show you 3 last ones before we do a little practice with this in the next video. And here's one in particular. Here's the integral of 5 pi over 6 square root of x with respect to x. And we'd like to find the indefinite integral, the antiderivative, the solution to the differential equation if this is a derivative. So what do we do? Well, the first thing I do is I try to write it so it looks like the power rule right up here. I want x to be in the numerator, and I'm going to have to do that with fractional exponents and sometimes negative exponents as well. Okay. So this is our rule. So what I'm going to do is I'm going to rewrite this. Now the 5 pi, you're okay. And 6, you're okay. The square root of x in the denominator, you're not okay. We're going to move you. In fact, you really mean that you're a negative 1/2 exponent. That's what 1 over the square root of x is with respect to x. So now I can go and use my power rule. So 5 pi over 6, you're still good. You're just going to come along. I'm going to add 1 to negative 1/2. That's going to make it a 1/2. I'm going to divide by that new power. So 5 pi over 6, still hanging out, being groovy. The second part, when we divide by a 1/2, that's the same as multiplying by 2. Gets us to there. And this 2 will go into this 6 3 times. Simplified 5 pi over 3, x to the 1/2, plus c, constant. Cookie on Sesame Street. Now, could we check it or derive it? See if you get the same thing. That's one. Second thing, let's say we have x cubed plus 5 over x to the 6th with respect to x. Aha! Surely I can take the integral of all 3 of these. Not so fast. We cannot do that. Because we have division, what I have to do is I have to put this x to the 6th underneath each term because it's a single denominator. Okay. Now, notice I have one integral symbol. That's fine. You could also write it separate, but if you do write it separate, you have to include the dx, the with respect to x each time. Okay. So just for your information. So let's simplify this. So this is really x cubed over x to the 6 is really 1 over x cubed, or x to the negative third. And 5 over x to the 6 is really 5x to the negative 6, all with respect to x. Let's power rule it. Don't celebrate yet. That integral sign is still there. You have not integrated the thing. All we've done is simplified it. So let's add 1, divide by the new power, and let's do it here too. Add 1, divide by the new power. Don't leave it like that. Don't leave it like that. We got negative exponents. So let's move things around. This is really negative 1 over x squared. And that 2 has to stay down there as well. And then negative 5 goes into 5 one time, or negative 1 times. And this is our final answer. So if we see multiplication or division, we have to do those operations. We have to fulfill that before we can move on. Speaking of multiplication, when we have it, we have to do it. You cannot integrate all 3 items and be good. So you're going to have to distribute. So that's really what, 2x to the 4th plus 16x with respect to x. So we'll keep the 2, add 1, divide by the new power. Keep the 16, add 1, divide by the new power. And simplify. So this is really 2/5 x to the 5th plus 8x squared plus c. In your text, should you have one, and you do, there is some reading in this chapter you can go ahead and do that might help you out a little bit as well. So that's an introduction to the antiderivative, the solution to a differential equation, and integration overall. We'll be back in a few videos coming up to let you practice and let you make sure you're on the right track with things, and to go ahead and figure out that C, not the cookie, the constant.